This week I want to discuss some of the results associated with making inference about the parameters in our simple linear regression model. You'll recall that the model is yi equal beta 0 plus beta 1 times xi plus this random error term, and we had lots to say about the random error term and its distributional behavior. We developed last week a mathematical way to compute these estimators B1 and B0 and subsequent estimates given a particular data set that we have available to us. We noted last week that B1 could be written as a linear combination of the y sub I, and B0 could also be written as a linear combination of the y sub I. We discussed the idea that these estimators were unbiased. We could in fact compute the variance of B1 and the variance of B0. That's all done for us in our textbook. If we assume that the random error terms are normally distributed, then the quantity B1 minus beta 1, which is its mean, divided by its standard deviation, is a standard normal distribution, has a standard normal distribution. And if we don't know sigma squared, which we often don't, and we substitute mean squared error, which is an unbiased estimator for sigma squared, in for it, then it turns out that the quantity B1 minus beta 1 divided by the standard deviation of B1 estimated, it has a t distribution with n minus 2 degrees of freedom. We lose 2 degrees of freedom because in our model we're estimating two population parameters, beta 0 and beta 1. For a discussion of this, you can see page 45 of our textbook. So now let's take a look. Now that we have an understanding of the distributional behavior of B0 and B1, we can in fact make some inference about those model parameters. One of the first things we see is that we can in fact, as we did in our statistics course, construct a confidence interval estimate for beta 1 using its point estimate, that is B1, plus or minus some stuff, and the stuff has to do with the level of confidence that we're interested in attaining and the variability of our estimator B1, that is the standard deviation of B1. And we can compute that standard deviation as the square root of mean squared error over the sum of the squares associated with the x variable. We denote it's the standard error of beta 1. Now, on page 45 of our textbook, some of this computation is done for us, but in fact, the Excel output provides this for us straight away. So if we go to our Excel output associated with our data from our monthly payments that we saw last week, and we take a look at that output, we see right here in this row, that is the row associated with the coefficient for debt, we see that Excel automatically computed for us the confidence level, a 95% confidence interval for the parameter beta 1. Our point estimate, as you'll recall, was 0.1243. That is our estimate B1. But we know because of the variability associated with that estimator, that is the standard error of B1, we can add and subtract to that point estimate to arrive at a confidence interval estimate for the parameter beta 1. So we're 95% confident that the average housing payment, monthly housing payment, goes up somewhere between 0.1098 and $0.1387 for every increase dollar in debt. And that's how we would interpret that. So again, I'd ask you to take a look at page 45 of our textbook for some details associated with that. The next thing we want to chat about, and again, all this is described in our textbook in great detail, is testing whether there's a linear relationship between x and y. That is, we want to test whether there's actually a slope or not. And so our null hypothesis is that there's no linear relationship, that is, that the slope of the line associated with our regression model is 0, pardon me, versus the alternative that that slope is not 0, which would be indicative of a linear relationship. And because we know something about the distributional behavior of B1, That is, we know that B1 minus beta 1 divided by the standard error of B1 has a t distribution with n minus 2 degrees of freedom. We can carry out a test of hypothesis. That is, we can construct a critical region associated with this two-tailed test, and if our test statistics value is in that critical region, then we would reject HO in favor of HA. Now again, Excel is just great for helping us get around this and actually do these computations. I do think it's important for you to do them by hand if you want to, get a good sense of how all of that works. But we also know that Excel will provide that in terms of our output. So here's the computed t statistic. This is the test value computed. 16.94, which is our 0.1243 divided by our standard error of 0.007, and that gives us a value of 16.94. So that's our test value, and we compare that against a critical value, or we can use the p-value approach for testing a hypothesis. And we notice that the p-value in this particular case is practically 0. So that means that if beta 1 equals 0, the probability of getting a test statistic of 16.95 or bigger is practically 0. So that's pretty good evidence to suggest that beta 1 must not be equal to 0. And so again, I would ask you to go through that, but understand that Excel actually provides that information for us. Now we talk about the power of the test, and the power of the test is discussed on page 51 of our textbook. I think it's important for you to understand what the power of the test is, and the power of this particular test is the probability of correctly rejecting HO if H1 is true. Well, in order to compute the power, then we have to have some idea of what H1 is. That is, we have to have some specific value of beta 1 in mind, and we also have to know the variance of B1. Again, take a look at page 51 of our textbook. Look at the example cited there. Make sure you understand how to use table B5 in the appendix of our textbook, and just give that a little bit of spin. Power, we're not going to be too concerned with its computation, but it is a very important construct, and one that you should certainly be familiar with. I just want to reiterate something that I had mentioned last week, and that is, when we're talking about simple linear regression models, we're trying to determine if there is a linear relationship between x and y, and that can be couched in this notion of correlation too. And so what I wanted to demonstrate with this particular slide was that testing whether beta 1 equals 0 or not is equivalent to testing whether rho, the correlation coefficient between x and y, is equal to 0 or not. And if you went through the arithmetic, you would see that those t-tests are exactly equivalent. So if one wants to determine whether or not there's a significant correlation between two variables x and y, you could run a simple linear regression model and equivalently test whether beta 1 equals 0 or not. Now I want to spend a little time talking about prediction. And of course, you're going to have to flush all this out by reading through the textbook, looking at the examples in your book, and also referring to some of the handouts that are provided within the lesson section of week 2 in our course. If we're interested in predicting the mean response for a given level of x, we simply use our fitted regression line and compute y hat at that particular value of x. Call it y hat sub 0, corresponding to the particular value x0. But we have to understand that y0 hat, it's a statistic. It has a distribution. And it turns out that the distribution of that statistic is normal. We know that its mean is beta 0 plus beta 1 times x naught, and we can determine that its variance is as you see on this slide. And so if we want to produce a confidence interval for the mean response of our associated with our simple linear regression model, We do the same thing that we did, all the time in constructing confidence intervals. We take the point estimate, y sub 0 hat, and we add and subtract some stuff to it. And the stuff that we add and subtract has to do with our level of confidence, our alpha, and the noise associated with making that particular or computing that particular value. That is the variance of y0 hat, or the standard deviation rather. And so we can again construct a confidence interval for the mean response using this notion that we've seen in our statistics course. For example, we might want to construct a 95% confidence interval for the mean monthly payment of those families that have $3,500 in debt, and I'll do that momentarily. Now, we might also be interested in constructing a prediction interval for a new observation. Now, this isn't the mean. This is predicting a new observation. And we'll denote that in this particular slide presentation as y hat sub h new, to remind you that this is a new observation. So in this case, we have to be mindful of the fact that there is another source of variability beyond that associated with the mean response. And again, this is discussed for us on page 58 of our textbook. I would ask you to take a look at it. The bottom line is we have another source of variation. I'll actually, I guess as I think about it, I'll actually put together a little live scribe lecture on how to compute the variance associated with making a prediction for a new observation. And you can look it over too. But our textbook, again, page 58, discusses these details. Now this is just a lot of arithmetic. And of course, Excel is great at handling arithmetic. And so what I have done, Excel itself does not have the capability to build these prediction intervals or confidence interval estimates for a mean response. But on this workbook called Payment SLR Solutions, which I will make available to you, there's a tab, a worksheet called CI Estimates, Confidence Interval Estimates. And I've built a little worksheet here that will allow you to enter the appropriate values associated with a simple linear regression model, the sample size, the degrees of freedom, the t-value associated with whatever level of significance you want to, level of confidence you want to embrace, the sample mean, etc. If you enter those values in cells B8 through B15, and then provide some particular X value and some particular level of confidence that you're interested in, then this little worksheet that I've developed will actually do the arithmetic for you. For example, you see X equal 3,500, but suppose I wanted to compute a confidence interval estimate for people with $4,000 in debt. I would simply type in 4,000. If I want to leave it at 95% confidence, and all I have to do is hit enter. And I know it's going to be difficult for you to see on this presentation, but notice that the numbers change interactively. So I've provided this for you. I would urge you to download this workbook and pay particular attention to this particular worksheet called Confidence Interval Estimates. Now keep in mind that we have certainly a wider interval when we're trying to deal with individual responses at a particular level of X, and that's obvious from the output here. Take a look at the confidence interval estimate for the mean response, 913 to 964, versus the prediction interval for a particular response of 382 through 1494. And if we go back to our 3500, which is what we had originally wanted to discuss, you see that the same holds there. So again, I'm trying to give you some highlights. You are obviously going to want to go back and read through your textbook to try to get a lot of the details. Now, the other thing that's discussed in Chapter 2 is the breakdown of the sums of squares associated with our simple linear regression model. And we recall this slide from last week's discussion. Typically, when we talk about variation, we're talking about a measure of dispersion of an observation of the observations about their mean, the y sub I minus y bar. Well, as you can see, the y sub I minus y bar can be broken up into two pieces. That is the y sub I minus y hat, and then what's left over, the y hat minus y bar. And so we can, in fact, break down the difference between an observation from its mean into two pieces. It turns out that if we square and sum both sides of that equation, we get the result that you see here. And we call these things the sums of squares total on the left, the sums of squares error we saw before, and the sums of squares for regression. And so we can break down and do an analysis of variance associated with the variation associated with our observations. The total sums of squares, the explained variation is what we sometimes refer to the sums of squares for regression as, and it's the amount of total variation accounted for by the relationship that we've built in it using our simple linear regression model. And then, of course, even if we were to use our fitted regression line, we would still have some variability. We call it the sums of squares error. That is, even if we were to use the point estimate associated with our linear regression line, our observation might not lie precisely on that line, and so we still have some variability that is unexplained, and that's the sum of squares error. Well, it turns out, and again, I might include this in a little write-up that I do in a LiveScribe lecture for you. Not sure. I mean, you can find it in various references. But notice that the expected value of mean squared error is sigma squared. We've already discussed that. And the expected value of mean squared error is sigma squared plus some other stuff. And notice, if beta 1 is 0, then that other stuff goes away, because we're taking beta 1 squared times the sum of the x sub I minus x bar squared. And if beta 1 were 0, then the ratio of the expected value of mean squared error, mean squares for regression, over the expected value of mean squared error, that is, this test statistic f's value, would be equal to 1. And so we have another way to test whether or not our linear regression model is significant. That is, we could take a look at the mean squares for regression over mean squared error, and if that value is close to 1, then we would most likely conclude that beta 1 is 0. On the other hand, if that value is removed from 1, then that gives us evidence that beta 1 is not equal to 0, in which case we would reject the null hypothesis in favor of beta 1 being something other than 0, which is evidence that there is a slope associated with our model, which means then that our model would be significant. And so you see this here on this slide. And again, this is all done for us in our Excel output. So I go back to that output associated with running the linear regression model using the data analysis toolpack in Excel, and I see up here this ANOVA breakdown. I see the sums of squares for regression, the mean squares for regression, the sums of squares for error, the residuals, the mean squared error. Notice, by the way, that the square root of mean squared error is the standard error of the estimate. So if you take the square root of 79,960, you get 282. We'll come back to that in a moment. But the bottom line is, for our simple linear regression model, our f-test gives us precisely the same p-value as our t-test. Practically 0. That is 3.31 times 10 to the minus 51. Pretty small. Notice also that for this test, if you were to take this t-value of 16.94 and square it, you would get the f-value of 287.26. And so we have another way to test whether our whether our model has an overall significance. Now, in a simple linear regression model, we could use the t-test, but in our multiple linear regression models, we're going to want to rely on the f-test. So more to come about that. And finally, I want to talk a little bit about the coefficient of determination. That is R squared. R squared is defined to be the sums of squares for regression over sums of squares total. Now, the sums of squares for regression is the amount of the variability in our observations that has somehow been accounted for using the line, by using the line. So we call the sums of squares for regression, alternatively, the explained error. That is, the error in our model, which is captured then, explained away then, by using our simple, it's the amount of error in our data, which is captured or explained then by using our model, as opposed to using the mean for a particular x level. And of course, the square root of R squared represents the correlation between the fitted values and the observed values of the response variable, and you can confirm all that by doing a little bit of arithmetic. I do want to mention to you that R squared is sometimes abused, and I don't want you to confuse the degree of linear association between x and y with the usefulness of the model. R squared alone does not provide an absolute measure of the appropriateness of a model. Look, we can have a high value of R squared, 0.9, but if we still have a lot of error, suppose we had 1,000,000 units of error and we explain 900,000 units, well, that still leaves 100,000 units of error unexplained, and that could be problematic. Now, R squared can be influenced too. The more variables we put in the model influences R squared. The spread of our levels of observation across the x values, that has some implication for the value of R squared. Large values of R squared do not necessarily imply that the model is accurate. Even though R squared might be big, the overall error might be so large that estimates used in the model may be of little use. And that's very important. As a consequence of the influence that additional variables might have on this coefficient of determination, some researchers, some statisticians have come up with an adjusted R squared value, which accounts for, notice in the denominator here, there's value p, that's the number of predictor variables in our model. And so this R squared adjusted, which also appears in our Excel output, accounts for this business of being able to influence the value of R squared through the inclusion of more and more predictor variables. So we'll take a look at it too. One final thing that appears on our output is the standard error of the estimate. The standard error of the estimate is the square root of the mean squared error. I've already alluded to it in this presentation. It's essentially the standard deviation of the residuals and gives us a sense of the spread about our fitted regression line. And we can expect about 2/3 of our observed y values to be within one standard deviation of the corresponding fitted values of y, and about 95% to be within 2 standard deviations. And again, this is computed for us straight away up here in the top part of the output associated with the data analysis toolpack regression procedure. Well, again, I've gone through this rather quickly, but the idea of these presentations is to present to you some of the highlights associated with the chapters in our textbook. By all means, I urge you to do the homework problems associated with this chapter. I certainly urge you to read through all of the details associated with the chapter, and to the extent that I make them available, any live scribed lectures or PDF files that I might also post in the lesson section of our course.